Okay, calculus, let's finish this off. There are many applications in physics and engineering, dynamics that involve the relationships among speed, arc length, curvature, and acceleration. I'm not a physicist or an engineer, so I will do my best to try to explain what's happening. I can do the math behind what's happening because I can work with formulas, but to explain what's happening, I'm not so great at. One such application is frictional force. A moving object with mass m is in contact with a stationary object. For example, a car going around a track. The total force required to produce an acceleration a along a given path is F equals mass times acceleration. But we know acceleration is this other formula. So mass times the second derivative of s with respect to t times our tangential vector plus mass times, so I'm basically just substituting a for the function of a up here, which we had. So plus mass times curvature times ds dt squared times the normal component of the acceleration. So in short, we know that this is mass times the tangential component of acceleration times the vector t plus mass times the normal component of acceleration times the vector n. Just a normal vector to the function. The portion of this total force that is supplied by the stationary object is called the force of friction. For example, a car moving at constant speed, rounding a turn, the roadway exerts a frictional force that keeps the car from sliding off the road. If the car is not sliding, the frictional force is perpendicular to the direction of motion, has a magnitude equal to the normal component of acceleration. As shown in this picture, the potential frictional force of a road around a turn can be increased by banking the roadway. But let's do an actual problem. A 360 kilogram go-kart is driven at a speed of 60 kilometers per hour around a circular racetrack of radius 12 meters, as shown to the right. To keep the kart from skidding off course, what frictional force must the track surface exert on the tires? Okay, so we've got mass. We need, so this is the second half of the component on the last thing. We have curvature, which is 1 divided by the radius. This is kilograms, 1 over 12 meters. And then we need to have ds dt squared. So that would be our speed squared. Now 60 kilometers per hour. We really like it to deal with meters per second. So how do we convert kilometers per hour to meters per second? So we've got 60. Take 60 kilometers per hour. That would be 60,000, I believe, meters per hour. But how many seconds are in an hour? 60 times 60, so 3,600. So that would be 60,000 over 3,600 meters per second. Let's take some zeros away. That's 600 over 36, which reduces to 100 over 6. So this is 100 over 6 meters per second, and that needs to be squared. So I'm gonna do something. 300 divided by 12 is 30. So we have 30 kilograms per meter times, when I square this, I get 10,000 over 36 meters squared per second squared. 30 divided by 36 is 5/6. One of the meters cancels, so we have kilogram meters. So it's now times, actually I'm just going to leave kilogram per meter, and we have 10,000 meters squared per second squared. So one of the meters is going to cancel. 5/6 of 10,000 should be 8,333.33, I'm just repeating, kilogram meters per second squared. This is how much force the track surface must exert to keep the go-kart from sliding. And that's the only problem in this section. Now, the rest of your notes here, it's a summary of everything from chapter 12, which will be formulas you can use. These should be helpful for you when you're going through problems on the review and then doing the test. So that's it for this section.